Hello. Okay, so hope you are all enjoying your 8 millionth snow day. And yeah, so I'm going to make this video and then we will kind of adjust our schedule a little bit, but this will make sure that we still get chapter 7 taken care of. Okay, so we ended last time with the um, there we go. We ended last time, we talked about moles and what that means. So I'm going to scroll back on our slides here. And remember, we talked about the atomic mass number or the atomic mass or the mass number on the periodic table, which is that one on the bottom. It can tell us two things. It can tell us the mass of one atom of that element in AMU. Remember, that's atomic mass units. Okay. Or it can also tell us the number of grams of that element that are in 1 mole. Okay. And remember, 1 mole is it's like a dozen, right? It's just a counting number. So 6.02 times 10 to the, let's see, I always forget this, 23rd. Okay, not 24th. For some reason, I always want to say the 23rd power, or the 24th power, I mean. But it's that many particles in 1 mole. Okay, that's a lot, right? Okay, so your homework was CC's 1 and 2. Okay, if you have questions about those, let me know. Okay, and remember that number, that mole number is Avogadro's number, okay, or Avogadro's number. Please, please, please remember that AMU, atomic mass units, are not the same thing as grams. Okay? Just like if you have a dozen, it is not the same thing as ounces. Okay? And we need to know how to work with moles because we're going to use them for the rest of the semester, which I know you're all thrilled to hear. Okay? So we're going to start off with a new definition, okay, a new word, molar mass, right there. Okay, so the molar mass of something is the mass of a molecule in AMU, or the mass in grams of 1 mole of a molecule. Okay, so we're going to use that term mm, periodically. See what I did there? Okay, so let's do an example. Okay, this is example 7.1. Okay, and this is on page 199. Okay, and this is the section entitled Mole Problems, not just in your backyard. Okay, so example 7.1 says, what is the mass of a single molecule of glucose? And they give us the formula for glucose as C6H12O6. Okay, so let's see. When they just ask us the mass, like it says, what is the mass? Generally, they're looking for AMUs. Okay. If I'm writing the problem, I will try to specifically say like what unit I'm looking for there. Okay. So what is the mass of a single molecule of glucose? So we've got carbon and hydrogen and oxygen. So we have 6 carbon atoms. We have 12 hydrogen and 6 oxygen. So we're going to find the mass of each of those types, then we can add them together. So 6 and carbon is 12.01 AMU, which gives us 72.06 AMU. And then we've got hydrogen, and hydrogen has a mass number of 1.01 AMU. So that'll give us 12.12 AMU. And then oxygen 6 times 16, whoops, AMU. And sometimes oxygen, I think we talked about this last time, sometimes oxygen Periodic table may call it 15.99, whatever. Okay, either you're going to have some rounding to do on these, and that's okay. All right. And depending on what periodic table you use, it'll round them differently. So we're going to add up all three of these, and we're going to end up with 180.18 AMU. Okay. So that's the mass in AMU of a single molecule of glucose. Okay. Now, the second part of the question says, if we have a sample of glucose, if I handed you a test tube or a flask, an Erlenmeyer flask or whatever, and said, hey, this is glucose, and I want you to figure out some things on it. Okay. So if I said, okay, it's got this many molecules, now I want you to figure the mass. Okay. So that number, 6.02 times 10 to the 23rd, remember that's 1 mole. Okay. And the molar mass is that number in AMU of 1 molecule, or in grams of 1 mole. Okay, so back here we figured the mass in AMU of 1 molecule, 180.18. Okay, 180.18 AMU. Okay, so the mass in grams of 1 mole is going to be 180.18 grams. Okay, so if you're looking at that in your book and or you're on a test or on homework and you're like, oh my gosh, this seems like that is a hard question, I'm just gonna skip it. I don't know what to do. You know what to do. Okay. It seems like it's almost like too easy to be the actual answer, but it's not. Okay. So let's look at example 7.2. Okay. So in example 7.2, we've got 15.6 grams of magnesium chloride. Okay, and I gave you the formula here, and we want to know how many moles. Okay, so first of all, we want to figure the molar mass of magnesium chloride. Okay, so we have 1 atom of magnesium. Okay, and magnesium is 24.31 AMU. And then we want to add 2 molecules or 2 atoms of chlorine. And each of those is 35.45 AMU. Okay, and we need to multiply that by 2 because there's 2 of them. So the mass of 1 molecule in AMU of magnesium chloride is 95.21 AMU. So we'll say 1 molecule. Okay. So how much does 1 mole weigh? So 1 mole of magnesium chloride in grams is 95.21 grams. Okay. So the difference between these two things is we're talking about either 1 molecule and how many atomic mass units, or 1 mole, which is a whole bunch of molecules in grams. Okay. So if he started out with 15.6 grams, so this is where we're going to do our dimensional analysis that we talked about at the beginning of class last week. So 15.6 grams, that's what we're going to start with. Let's switch to a different color because I was just kind of tired of that color. Let's go with blue. Okay, so 15.6 grams. Oh my goodness gracious. Totally lost my train of thought. Okay, 15.6 grams of magnesium chloride. Okay, so now we're going to use that conversion factor. And our conversion factor this time So we want to get rid of the grams of magnesium chloride. And so we have grams of magnesium chloride on the bottom. And then on the top, we're going to put the unit that we want, which in this case is moles of magnesium chloride. Okay. So so in 1 mole of magnesium chloride, we need to know how many grams, which is what we figured out back here, 95.21. And that, whoops, goodness gracious. Okay, 95.21 grams of magnesium chloride. Okay, so when we get ready to multiply this, remember this is the same thing. Oops. If this was over 1, and when you're multiplying fractions, you just go straight across. Okay, top to the top, bottom to the bottom. You leave the top numbers on the top, bottom numbers on the bottom. Okay, so in this instance, we would have 15.6 grams times 1 mole divided by 1 times 95.21 grams. Okay, and you don't have to write all that out. I'm just reminding you what we would do. Okay, so our unit grams are going to cancel out, and basically we're going to have 15.6 divided by 95.21. Okay, if you put that in your calculator, you should get 0.164 moles of MgCl2. Okay, now if we're looking at that and we think, okay, up here I got that 1 mole is about 95 grams. We only have 15 grams, so we should get much less than a full mole, right? We got like less than a fifth of a mole. Okay? Okay, I was about to go questions, but you're not here. So if you have questions, write them down and bring them to me. Okay, now if I look back at example, it says how many moles does he have? And then there's one more part. Oh, just kidding. Okay, so I ran out of room. We're going to call this one the moles page. Moles. And then we're just going to add a page. And we're going to figure how many molecules he has now. Okay, so we had 0.0164 moles of MgCl2. Okay, and we want to figure out how many molecules that is. Okay, so moles is going to go on the bottom because we want to get rid of it. And then on the top, we'll put molecules. Now, what conversion do we have that goes from moles to molecules? Well, guess what? It's Avogadro's number. Yay. So 1 mole, and then here we'll have 6.02 times 10 to the 23rd. Okay, so we've got moles on the top and moles on the bottom. So those are going to cancel out. And we're going to end up with 0.164 times 6.02 times 10 to the 23rd molecules. Okay. And again, if you need help putting those in your calculator, I'll be happy to help you. So if we multiply that out, we're going to get 9.87 times 10 to the 22nd molecules, which is a smaller number than Avogadro's number, which we should get because this is a smaller number. Okay. Okay. So let's look at example 7.3. And I know that it probably seems like I'm going really fast because I'm not pausing for questions, but you can always pause the video and write down questions you have, or go backwards and watch it again, or come and see me and ask me questions. Okay. Okay, so example 7.3. So this is on page 201 in the yellow box. A chemical calculation indicates that a reaction should produce 12.119 moles of nitrogen gas. How many moles is this? That's not what that should say. This should say grams. Okay. So how many grams is that? So if we're going to start with moles, we want to go to grams. All right. Let me pull that out. All right. So, sorry, lost my train of thought. So I was talking about something else. All right. Now, here's the deal. Let's think about, first of all, we have to think about nitrogen gas. What do you know that's special about nitrogen? Okay. It's that it's in that 7 section on our periodic table that makes the 7, plus there's one more. Remember that always want to exist as 2 molecules together. So nitrogen is a homonuclear diatomic. Okay. So in 2. And so when we look at finding the molar mass of nitrogen gas, 14.01 AMU times 2. And we're going to get 28.02 AMU is the mass in AMU of one molecule. Okay. So now we know that 1 mole of nitrogen gas has a mass of 28.02 grams. Okay. So that's going to end up being our conversion factor. Okay. 1 mole of nitrogen gas is 28.02 grams. So we started out with 12.119 moles of N2. Okay. That should say molecules. Okay. No. Oh my gosh, that should say grams. Duh. Oh, sorry. There we go. Okay. Let's try this again. All right, this should say grams. I was gonna say, I don't know why I need 2 slides to figure out that. Okay. So now let's do our conversion factor. We say, okay, 1 mole of N2 has a mass of 28.02 grams. Okay. Um, so when we go to multiply these, we have moles on the top and moles on the bottom. So that's going to cancel out. Okay. And then we have 12.119 moles times 28.02 grams. And we should get 339.57 grams of N2. And that is our final answer because it was asking for grams. All right. Okay. So take a minute to think about that. Pause it if you need to. And those examples are like CCs 3 and 4, okay, that are going to be assigned for next week. Okay, and there will be, if you start working on them and you're like, oh my gosh, I have no idea what's happening, then yeah, obviously I'm not going to be like, I can't believe you didn't turn that in. So do your best. Okay, the next section in your book, right after CCs 3 and 4, is called Using the Mole Concept, pages 201 to 204. And that includes CC number 5. Okay, all of that we're going to skip. So don't worry about reading those pages or doing those pages or anything. So that includes experiment 7.1, which is not very fun. So we're going to skip ahead to right after CC number 5. And this section, it's on page 204. Right about the middle, it says moles infesting chemical equations. I just love these cute little names that they have for the chapter or for the sections. Okay, so this chemical equation right here, N2 plus 3H2 yields 2NH3. We have a couple different ways we can read that, okay? Right now, we have 2 different ways we can read that. We're going to later on we'll learn one more, but that's going to be in a future chapter. Okay. So one way that we can read this, looking at the coefficients there, the numbers in front, is we could say that one molecule of N2 or nitrogen reacts with three molecules of H2 or hydrogen to yield, can I spell that white I? I think so. Or produce two molecules of NH3. Okay. Now, another way that we can read that using what we've just learned is 1 mole of N2 reacts with 3 moles of H2 to yield or to produce 2 moles of NH3. Okay, so the only difference between the two ways that I read those was molecule and mole. Okay. You can do either one. Now, you can't mix it though. You can't say 1 molecule of N2 reacts with 3 moles of H2. Like, no, you got to keep it the same units. Okay? So we can use chemical equations like this to determine the amount of products and reactants that we're going to need. Okay? Like we can say, okay, we're going to start with this amount. How much are we going to get? Or we know that we need to produce this amount over here. How much do we need to use to react? Okay, I'm looking for a drink because, yeah, there we go. Sorry about that. Okay, so example 7.4. We've got this equation. We've got hydrogen peroxide, okay, H2O2. So we've got 2 moles of H2O2 decomposing 2 moles of H2O2 decomposing to make 2 moles of H2O, which is going to be water, and 1 mole of O2, which is going to be a gas. So we can write a ratio here of moles. We can say, okay, so I know that 2 moles of H2O2 are going to produce 2 moles of H2O. Now, it's a like 2 over 2 is the same thing as a 1-to-1 ratio, right? It's the same number. We can also say 2 moles of H2O2 yields 1 mole of O2. Okay? You can also, you can flip these over, like switch them based on what you're trying to find out, what you're given, what you're trying to find out, because this is going to um, excuse me, this is going to be our conversion factor in the problems that we're getting ready to do. Okay? So if I've got this example 7.4, and I say how many moles of oxygen and water can be made from 12.18 moles of H2O2. Okay, and it's the same equation that we had up here. All right. And so I'm just going to rewrite our equation. So we've got 2 H2O2 yields, let me make sure that I get this right. 2 H2O plus O2. Okay. Yields 2 H2O plus O2. Okay. So we're doing that dimensional analysis again, just using our ratios or, yeah, our ratios as a conversion factor. Okay. So if I say, okay, I started out with 12.18 moles of H2O2. So 12.18 moles H2O2. And then I'm going to say, okay, so on the bottom, I want to put what I'm going to get rid of, moles H2O2. And on the top, I'm going to put what I want. So how many moles of oxygen and water. So I'm going to do the water first. So moles H2O. Okay. So those two coefficients are both 2, okay, or a 1-to-1 ratio. Now, here's the deal. So let's see what we're going to be able to cancel out. We've got moles of H2O2 cancels out, right? And we end up with moles of H2O, which is great because that's what we want. Now, we have 12.18 times 2 divided by 2. 2 divided by 2 is the same thing as 1. Okay, since it's a 1-to-1 ratio, you're going to need the same amount, 12.18 moles of H2O. Okay, so now let's look at how many moles of oxygen we're going to need. There we go. So again, I'm still going to start out with 12.18 moles of hydrogen peroxide because that's what they gave us in the problem. Then I'm going to use that conversion factor. I'm going to start out on the bottom with moles of H2O2. And then on the top, I'm going to have what I'm looking for, which is moles of O2 this time. And so now we've got 2 moles of H2O2 and 1 mole of O2, right? So let's see what's going to cancel out. Moles of H2O2 is going to cancel. And so now we've got 12.18 times 1 divided by 2. Okay? Or 12.18 divided by 2, right? Because times 1 doesn't do anything. Okay? And so this is going to give us 6.09 moles of O2. Okay? And then I think I have another page here, but I actually don't need that. Sometimes I just can't gauge how much room I need. Okay, this is an example that we're going to do. This is not listed as an example in your book. Okay, and I don't remember, it might be a CC. No, it's not a CC question. I don't actually know where I got this. This was in my notes from the last time I taught this. So I don't know. Okay, in this example, we have methanol and we're forming methanol. Okay, so the formation of methanol is described by this equation. 2C plus 4H2 plus H2O yield 2CH4O. Okay? So we've got 2 moles of carbon reacting with 4 moles of hydrogen, reacting with 1 mole of oxygen to yield 2 moles of methanol. Okay? And if we want to make, oops, drop my pencil. If we want to make 100 moles of methanol, how many moles of each reactant do we need? Okay? So we're going to do 3 different conversions because we have 3 different reactants. So we're going to start with 100 moles and let's see, of CH4O. Let's start with carbon, okay? So we're trying to get rid of moles of CH4O and end up with moles of carbon, okay? So moles of CH4O, up in our problem, that coefficient is 2. Moles of carbon is 2. So we're going to cancel out moles of CH4O, and then we've got 2 over 2, which gives us 1, right? And so we're going to end up with 100 moles of carbon, okay? That's the same because it's a 1-to-1 ratio. Let me see how many pages I have. Okay. All right. So let's go to the next page to do hydrogen. Okay. So our equation is 2C plus 4H2 plus O2 yields 2CH4O. Okay. All right. So we already did carbon, so let's do hydrogen now. So we started out with 100 moles of CH4O, and so let's put moles of CH4O on the bottom, and we're trying to get to moles of H2 now. And our moles of CH4O is 2, moles of hydrogen is 4. Okay. So let's see what's going to cancel. We've got moles of CH4O divided by moles of CH4O, goes away. Sometimes when I like go like that, because it's glaring in my glasses, it kind of looks like I have the crazy eyes. Or maybe I just have the crazy eyes. Alright, so 4 divided by 2 is 2. That looks confusing. Let me fix that real quick. Okay, there we go. Because it looks like I'm saying that's a 2 on the bottom, and it's not. So, if we have 4 moles of H2 and 2 moles of CH4. So if we have 4 on the top and 2 on the bottom, we've got 100 times 4 divided by 2. Okay? Or this can simplify to give us a 2 there. So 100 times 2, we're going to have 200 moles of H2 that we need to react in order to get 100 moles of CH4O. Okay? And that makes sense because the coefficient in our original equation here is 2 for CH4O and 4 for H2. Okay? And so we need twice as much H2 as we're going to get CH4O. All right, so one more. Actually, I'm just going to do this one on the same section. So let's do oxygen now. So 100 moles of CH4O, and on the bottom we'll have CH4O, and then on the top we'll have oxygen. And it's 2 moles of CH4O, just like always, and 1 mole of oxygen now. And so what's going to cancel? Moles CH4O, and now we have 100 times 1 divided by 2. So we have 100 divided by 2, and we're going to end up needing 50 moles of O2. Okay? So basically, when we're doing these problems with these ratios, it's very similar to scaling up a recipe, like if you like to bake, okay? Because, so say, okay, I'm going to make some muffins from scratch. And a regular muffin recipe makes 12 muffins. And you say, well, I actually want to make 48 muffins, okay? And so if we say 12 muffins requires 6 eggs. No, sorry. We'll say 2 eggs. How many eggs for 48 muffins? Okay. You probably instinctually know how to do this because you say, okay, well, 12 times 4 is 48. 12 times 4 is 48. So I'm taking the whole recipe, multiplying it by 4. Therefore, I need 8 eggs. Yeah, that's the same thing we're doing, except we're dealing with moles. Okay? So don't let the fact that we're dealing with moles and something you can't actually see throw you off. Okay? Now, here's a note at the bottom of this page. So sometimes in a reaction, you have reactants that are not used up totally. You might, some of them might be, they might all be, but there will always be at least one that is totally used up. Okay. And if you have, that's what we're going to talk about next, is if you have one that runs out and others that don't. Okay. But this is experiment 7.2. We were going to do it in class, but since you guys aren't here, we will do it next week. Okay. So we'll talk about that next week. Okay. We're going to talk, let's see. Let me see how far I wanted to get. Yeah, so I wanted to talk about limiting reactants a little bit. Okay. When you have a reaction and you have different amounts of reactants, and whichever reactant runs out first is going to limit how much product is made. It's going to limit the reaction. It's going to limit how many times it can proceed, how much it can go. So therefore, we call it the limiting reactant. Okay. The reactants that are not limiting reactants, that like there are some left over, those are generally called in excess, meaning we have excess, we have extra of these. Okay. Like back in our muffin um, example. So if we said, okay, if our muffin recipe, we said it needed 8 eggs, right? So if our muffin recipe needed 8 eggs and 2 cups of milk, okay, so we'll say we have 10 eggs and 2 cups of milk. So when we're making those muffins, that milk is going to run out first. We're going to have eggs left over, right? We're going to have 2 eggs left over, but the milk is going to run out. And if the milk runs out, you can't make any more muffins. So milk in that instance would be our limiting reactant, and then the eggs would be in excess. Okay? And so when we do our experiment 7.2, we will talk about which reactant in that experiment was our limiting reactant. Okay? So let's look at this example, and then we're going to be done with yapping about this. Okay. So this one, there is a limit. This is the section in your book on page 206. Okay. So let's say we're burning coal according to this equation right here. We have solid carbon reacting with oxygen gas to yield carbon dioxide gas. Okay, this is a very simplified equation for burning coal. That's not, we don't need to worry about that right now. Okay, in the equation that they've given us, there's 1 mole of carbon reacts with 1 mole of oxygen to yield 1 mole of carbon dioxide. Okay, so looking at question A, if we have 3 carbon atoms and 2 oxygen molecules. So remember that these numbers in front of our chemical equations, like the 1 and the 1 and the 1, these are all ones, right? Those can represent moles or molecules or atoms, okay? So we could also say 1 carbon atom reacts with 1 oxygen molecule, because remember it's O2, it's a homonuclear diatomic, to yield 1 carbon dioxide molecule. So it's a 1-to-1-to-1 ratio. So if I have 3 carbon atoms and 2 oxygen molecules, which one of those is going to run out first? Well, we know each time that reaction proceeds, it needs 1 of each. It needs 1 carbon, 1 oxygen. Okay, so we say carbon, 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 O2, O2. So those first 2 lines, these are going to get used up. Those will react, and then we're going to be left with some carbon. And remember, what we're left with is called in excess. And then our limiting is our O2, because it runs out first. So look at B. If we have 3 carbon atoms and 3 oxygen molecules, so C, 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 O2, O2, O2. All right, which one? So we're going to use this one, this one, this one. They both ran out at the same time. So there's no limiting reactant. And that can happen. Like, what a happy thing, right? If you're having a reaction and your reactants run out at the same time. That's great. You don't have anything left over. You didn't waste anything. Okay? What if we had 3 carbon atoms and 4 oxygen molecules? So we'd have carbon, 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 O2, 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 O2. Okay? So those. We're left with oxygen in excess, and carbon is our limiting reactant. Okay? Basically, to figure out which element is your limiting reactant, just see which one's going to run out first. Okay. CC number 7 goes with that. Let's see. Okay, so 6 was converting. Okay, CC number 7 goes with that, but it's about the experiment. So I'm not going to assign that yet. So, and I will, I'll put this on Google Classroom and I'll text it out also. And if I don't, just remind me. So your homework this time would be CC's numbers 3, 4. Remember we skipped 5 and 6. Okay. Yeah, if you have any questions, please let me know. It seems like we have a lot left to do in this chapter. Um, hmm. Let me think about. This is already pretty long, so I'm gonna go ahead and stop there, even though I would like to go one more. But I'm gonna stop there for now, and yeah, let me know if you have questions, and otherwise, I will see you next week.